In this video, we are going to demonstrate the built-in force control feature on the Titan Nexus servo controllers using a robotic gripper driven by a stepper motor with an incremental encoder. Here we have a Nexus SCX and a 24-volt DC power supply. Communication with the PC will be done with a USB cable. Let's go to the communication screen and confirm the communication. Next, we will go to the motor parameters screen. Let's open and download the pre-made motor database file for this NEMA 11 stepper motor. Note that the motor database file contains all the electrical and mechanical parameters for this particular motor. We can see the rated voltage and current and the maximum current that can be used in acceleration and deceleration. You can also see the electrical parameters of this particular stepper motor, the motor EMF constant, resistance, and inductance values. Let's go to the mechanical parameter page and see the motor inertia, viscous, and Coulomb friction values. Also see the maximum speed that can be reached with this motor. Before we exit out of the motor setup screen, let's store the parameters to the flash so that the values are stored permanently in the Nexus controller. Let's go to the configuration screen to change the motor direction to inverted. Let's go to the test drive screen and try servo on and do some slow motions to confirm that the motor parameters are good. But note that we are using only the motor mechanical parameters, so performance is not optimized yet. And also be careful not to hit the mechanical limits. Now that we know that the motor parameters are good, let's determine the new mechanical parameters for the whole system, which includes the gripper finger mechanism. Let's go to the tuning screen. Here we can enter the mechanical parameters manually, or use the Auto Detect wizard, which is what we will do. Click the Auto Detect button. Read and agree with the terms. Since we have a short stroke for this gripper, we will use the soft limit so that the fingers do not hit the end hard limits. Manually move the motor to the minus limit and reset the position as 0. Move slightly out of the minus limit and use that as the minus soft limit. Move to the positive end and move in slightly from the maximum position and use this position as the plus soft limit. Enable the soft limit check. Also, note that you can enable and jog the motor to set the limits. Since the mechanical parameters are not optimized, use slow motion to move and set the limits. Click Next. For the auto detection, we will start the move acceleration of 20,000 and decrease the detection increment amount. Note that the higher the acceleration, the better the results will be. So start out from low and work your way up to higher acceleration values. Now let's run the auto detection and wait for the auto detection routine to complete. Now we have the new auto-detected inertia, viscous friction, and Coulomb friction values. Click Apply and try the auto-detect again. Note that the mechanical parameters are estimated by looking at the motion performance, so the values are not exact but should come close to the desired values. Again, as mentioned before, the higher the acceleration value, the better the estimation will be. Click Next and close the window. Titan software has other tuning features as shown on the tabs, such as the Bode plot generation, cycle motion, performance monitoring, and auto gain selection and optimization. You can check out other tutorial videos for the auto gain tuning and optimization features. Now, let's go to the test drive and try to perform some motion. First, let's disable the soft limit and servo on the motor. Also, make sure to set the current and position error monitoring so that the motor is protected from using continuous overuse of the current. Let's put the first target position to 100 and speed to 10, and acceleration to 2000. Let's put the second target position to 4,000 and keep the same speed and acceleration. Let's try to move the motor to position 1 and 2 and see the motion performance. Since this gripper does not have a home sensor, let's perform the hard stop homing using current sensing. Let's open a pre-written hard stop homing program and let's review. First, we turn on the servo. Wait for the servo on to complete. Set the high speed to 2. Set acceleration to 1000. Jog the motor in the negative direction. Look for the current to trigger at 300 milliamps in the minus direction. As soon as the trigger is detected, stop the motion. Set this position as negative 100, and then move to the 0 position. Let's run this program and we can see that the motor finds the 0 position by going to the negative hard stop and moving out slightly and then setting the position to 0. Now let's perform the force control. First thing that we will do is to set up the force control parameters. Let's enter the start search position value to 2000, velocity to 80, and acceleration and deceleration to 2000. Let's set the current to 500 milliamps, which is the maximum current that will be used when moving to the start search position. Again, this current value does not mean that the value will be used all the time, but this is the current limit value. Next, let's enter the search motion values. For maximum search position, enter 4000, which is the maximum position to move to find the current trigger. For the search velocity, enter 10 and acceleration as 3000, and enter the current value to 500 milliamps. Let's set the current trigger value to 300 milliamps. While it is moving to the search region, if the current goes over this amount, the current detection will be determined as successful. Set the post trigger to 300 milliamps. This is the current to apply after the current trigger is detected. For our case, this value is the same as the current trigger value. Let's enter press time as 2000 milliseconds. This is the amount of time to hold after the current trigger is detected. Set the press delta to 0. This is the additional amount to move after the trigger is found. For the trigger action, let's select immediate back to trigger position, which means as soon as the current trigger is found, the motor goes back to the detected position. Other options include decelerate to stop, move back to trigger detection position, and so on. Since the press time is set to 2000, as soon as the trigger is detected and fingers go back to the trigger position, it will wait 2000 milliseconds and then do a pull-out motion. For the pull-out values, let's enter 1000 as the lift delta position. This is the amount of motion after the trigger action is finished. For the pull-out velocity, let's enter 20. For the move to initial position, let's enter 0 for position, 300 for velocity, and 5000 as acceleration. This is the motion after the pull-out motion is complete. Click Download. Let's enable the force control and start. You can see that the fingers move to the start search position and then starts the search motion at 10 RPM. It is looking for a 300 milliamp current trigger. When it does not find anything, you can see that the detected position color is red, and the finger moves back to the initial position 0 immediately. When it does find the current trigger, it maintains at the trigger position and holds for 2 seconds and then performs pull-out and goes back to the initial position. Let's check the Wait for Acknowledge checkbox. With this feature, the gripper will wait for the user to acknowledge before releasing the detected object. Let's save the force control parameters to Flash and also to a file. Now let's try the force control routine from the standalone A-script program. Let's open a pre-written force control program. In this program, we will run the force control routine 5 times. If the force detection is successful, we will turn on the LED. If it fails, we will turn off the LED. Let's review the program. Set the high speed to 10, move to 0 and wait for the move to complete. Turn on the force control. Set the cycle counter V1 to 0. We will loop the following in the while loop while the V1 counter is less than 5. Start the force control. Wait 100 milliseconds. we will wait for the force control result. If the force control result is 1, this means it found the force trigger. We turn on the LED and wait 1 second. If the force control result is not 1 and the trigger is not found, we turn off the LED and wait 2 seconds. Here, we wait for the force control stat to complete since it may take time to move back to the initial position. We increment the counter and continue the loop. After 5 cycles, we go out of the loop, turn off the force control, and turn off the LED. For detailed information on force control, please check out the force control application note. I hope that this force control tutorial was helpful. Thanks for watching the Titan Force Control tutorial video. If you have any questions, please send an email to support@arcusservo.com.